Hello everyone, we continue the third session of linear algebra in the course of deep learning. Uh, we have seen in the second session, on the second part, the concept of matrix rank and also the column vectors or the basis of column vectors. And today we continue and let us start with the concept of matrix transpose. We in the first session we saw already what is the meaning of or how to perform vector transpose, but what about matrix transpose? So in general, that if we have like a matrix with A11, A12, A13 and so on. So if let us assume only 3 elements here, so here we have E21, A22 and A23, A31, A32, A33. Usually the first number represent the row number and the second index represent the column. Okay, so for example A32 means that we are in the third row and the second column. Okay, and now when we make transpose, simply we swap between the column and rows, and then if this is matrix A, this is matrix A. Okay. Then A transpose will be just make every row as a column, then it becomes like that. So this row becomes column, so it becomes like A11, A12, A13, and this one becomes A21, A22, A23, yes, and also this one becomes like from row to column, then it becomes like A31, A32, and A33. You can see here that that the diagonal stay as it is. As you can see, it is the same, but each element just it is swapped. So A21 goes up above the diagonal A21, and A12 becomes under the diagonal, and so on. So this is the transpose process for matrix, and it can be performed for any matrix, not necessarily to be square matrix like 3 by 3 or 4 by 4. It can be for any m by n matrix. It can be done this transpose, and it becomes n by m. Okay. Okay, before we leave this one, let us take a numerical example. So if we have, let's say we have a numerical example 1 1 2 and 3 0 1. Okay, and you can see that this matrix A, it has 2 rows and 3 columns. It is 2 by 3. So the transpose of this matrix, it becomes directly 3 by 2, like this way. So it becomes 1 1 2 and 3 0 1. Okay, and in general, because for any matrix A belongs to like R real numbers, or it can be complex number, whatever, but is n by m, then A transpose becomes like part of, or it can be the dimension is m by n. Okay, so you can see that it is always possible to multiply A by its transpose. So A times A transpose is possible to be done for any dimension, because it will be n by m times m by n, so those are the same. So and the result will be matrix of n by n. And also the reverse is possible, so you can make A transpose times A, and in that case it will be m by n multiplied by a matrix with a dimension n by m, so the result will be a new dimension with m by m. Okay, so if we apply this for this example, if we multiply A times A transpose, then this will be, this is A. Okay, it will be, of course, because it is 2 by 3 and this one is 3 by 2, so the result will be a matrix with dimension 2 by 2. And the elements here, you multiply, like this is the multiplication of matrices, you multiply row by vector. So we take the first row, it is 1 1 2 times 1 1 2, so it will be 1 times 1 is 1, plus 1, it is like dot product, 1 plus 1 is 1, so the summation is 2. 2 times 2 is 4, then it will be 2 plus 4, the result will be 6. Okay, and then still the first row with the second column, it will be 1 times 3 is 3, 1 times 0 is 0, 2 times 1 is 2, so it will be like 3 plus 2, so it will be 5. Okay, and for the second row, we take the second row from the first matrix, so it will be 3 0 1 times 1 1 2, so it will be 3 times 1 is 3, plus 0 is 3, and plus 2 is 5. Okay, and 3 times 3 is 9, 0 and 1 is 10. Okay, so this will be the multiplication of A times A transpose. You can see that it is always true that when you multiply any matrix by its transpose, it will the resultant matrix will be symmetric. As you can see, it is symmetric matrix, means that all elements are identical with the corresponding position. For example, A21 will be the same as A12, A31 will be the same as A13, and so on. Okay, so they are called symmetric matrix, and only the diagonal can be different. Okay, but the others will be the same. Okay, and actually symmetric matrices has very important application in machine learning in general, because the covariance matrix, usually when we deal with data, the covariance matrices are symmetric matrices. Okay, and there are very nice rules to solve symmetric matrices. It can be much easier to find the inverse, and also the decomposition of symmetric matrices, as we will see them in details later. Okay, and okay, and now after this introduction about matrices transpose, let me define the identity matrix. Okay, what is the identity matrix? Identity matrix, usually represented as with letter I, is the unit matrix which consists of 0 everywhere except the diagonal elements which is like filled with or filled with ones. It is like that. For example, if we have, let's say, 3 by 3 matrix, identity matrix usually square, so they should be square matrix, so it is 1 0 0 0 1 0 and 0 0 1. So this is called the identity matrix. Okay, identity matrix. So and when we multiply invertible matrix A with its inverse, then the result will be the identity matrix. Okay, so if we have, let's say, matrix A, any matrix A, but it is invertible, because we have conditions to have invertible matrix, we will talk about them later. So if this matrix is invertible, then when we multiply A by A inverse, then the result will be I matrix, which is the identity matrix as it is shown here. Actually, in a scalar, it is equivalent to number 1. Because if you multiply any number except 0, of course, if you multiply like 5 times its inverse is 1 by 5, then the result will be 1. So this is the identity of the scalar, and the identity of matrices is given by this form. It can be general, as I said. It must be square, but it can be for any n by n matrix. Okay, so this is called the identity matrix. And before I continue, I like to clarify one point here. to understand, not only to increase our capability or our abilities to solve problems, but also to understand what this means. Actually, if we have like a 2 by 2 matrix, assume that our matrix A is the identity matrix, is 1 0 0 1. Okay, what this mean? This means that we have this is the our first element, so it is in this direction, it is 1, and in this is the first vector, so the first vector is 1 and 1 0, it is 1 in x axis, for example, and 0, and the second column is 0 and 1. Okay, so it is like this one, so it is 1 and 1. Okay, now this is like the conventional like space of in two-dimensional, okay, space. Now what happens if you multiply this matrix A by vector x, and this x now is equal to x1 and x2 for any two elements x1 and x2. Okay, so what this will be, so simply it will be like you can make like row multiplication, or you can make it like column multiplication, as we explained in the previous session. But if we do it with in the conventional way, as row multiplication, then it will be like 1 0 0 1 times x1 x2. Okay, before you make any multiplication of matrices and vectors, or matrix and matrix, always check that it is it legal to multiply or not. So it is, you can see this matrix 2 by 2 and this vector is 2 by 1, so it is legal to multiply, as you can see, because the number of columns of the first matrix is the same as the number of rows in the second vector. So the result will be also 2 by 1. So the result will be 1 times x1 is x1 plus 0 times x2 is 0. So the result will be x1, and for the second element will be 0 times x1 is 0 plus 1 times x2 is x2. So in general, when you multiply identity matrix in any vector, the result will be the same vector. For example, if we have x1 and x2, let's say x1 is 2 and x2 is 3. Okay, so now this is the vector, it is 2, and here let's say that it is 3. So we have this vector now. Okay, this vector x should be straight. Okay, now this is the vector x. When we make mapping of this vector x in the space of the represented by the matrix A, because the matrix A is the unit is the identity matrix, which is already here, where origin or the matrix the vector x is already there, so it will not change it. It will not change it. So this is the reason that when you multiply any vector with by the identity matrix, it will not change, it will not rotate the original vector, and it will not scale it as well. So it will generate the same, exactly the same vector. Okay, so look to it in this from this perspective, that we project the vector x in the same space where it is already. So it basically it will stay as it is. Basically it will stay as it is, it will not change. However, in general, for any matrix A, when you multiply it by vector x, as we explained in the previous session, it means that the linear mapping of x in the space A, in the space A, it will generate another vector b, and the vector b will be a rotation, a scaled rotation of the original vector x, and this is a rotation, and the scale, the rotation behavior and the scale value is determined by the behavior or the elements of the matrix A itself. Okay, so the matrix A, this process is called linear mapping of x in the space, on the new space of A. Okay, however, if A is identity or identity matrix, it will be the same. So if A is identity matrix, A times X will be X. Okay, so this is important to remember because we will use this concept later on in more like deeper analysis as we will see soon. Okay, now let us go to other topic, other related topic. Okay, and okay, let's have a new slide. Okay, yes, if we want to solve equations like this one, it is linear system of linear equations. For example, 3x1 plus 5x2, okay, equal to 1, and maybe x1 minus x2 equal to 5. Okay, you know that this kind of equations are very like commonly used in practice, and we have now two equations into two unknowns, and the relation between the parameters and the unknowns are linear, as you can see them, and we like to find what is x1 and x2, which will achieve both equation 1 and equation 2 in the same time. This could be done as in linear form, so you can define it in this compact form, ax equal to b, and then you can put the matrix A, the elements here, so it is 3 5 becomes 3 5, and 1 minus 1 1 minus 1, okay, multiplied by x1 x2, and this equal to b is 1 and 5. It is simply like that. It is simply like that. Okay, so of course we have different ways how to solve these linear equations. Of course, in case of two equations into two unknowns, it is very straightforward and can be solved, like in elementary school or primary school. They know how to solve this one. But of course, if the dimensions increases, then we might need like some advanced calculator or computer package in order to solve a system of linear equations. However, that there are some conditions, of course, for this solution to exist. Okay, for example, here we can say that x equal to A inverse times b, and in that case we have the conditions of A inverse. Actually, we already mentioned about the important conditions of A inverse to exist, that A must be non-singular, or in other words, the rank of the matrix A should be full rank. So here we have 2 by 2, so the rank of A must be 2 in order to find the in order that A inverse to be exist. Otherwise, it can be singular matrix where A inverse is not exist. And actually the reason for that, when the matrix A is non-singular, it means that they are independent. You have independent rows and independent column, but if it is singular, it means that we have dependency, and when we have dependency, then the inverse is not exist, and then we cannot find a single solution for the point x. Okay, this is very general talk, or very general representation of the problem, but let us take like some numerical example. Let us take the same example here, but I will change just small numbers. So let us say that we have 3x1 plus 5x2 equal to 1, and the second equation is nothing but just linearly dependent on the first equation. So we have 6x1, you can see that we multiply this by 2, and then if this is plus 5x2, I will make 10x2, okay. Then let us keep this 5 as it is, so equal to 5. Actually, this matrix, as you can see, the first equation is 3x1 plus 5x2 and equal to 1, and the second equation is nothing but just multiplied by 2, so we have 6x1 plus 10x2. So what will be the result? The result actually should be 2, because we multiply this by 2, so the result should be 2. So when we have 5, it means that there is no solution. There is no x1 and x2 that can solve this equation. Okay, it does not exist. We don't have solution x1 and x2 which can achieve both equations in the same time. Okay, and this is the reason that A inverse is not exist. If you put A in this way, like 3, 5, 6, 10, okay, this equation doesn't have inverse, is not exist. The inverse here is not exist. Okay, if you try to do it with in some package, you will find that the result is error. You will get error result, or they tell you the package that it does not exist. Okay, so and in that case it is important to remember that for system of linear equations, in order to have a solution, that it should be full rank. And the second condition, to have a single solution, then the matrix or the number of equations should be as the same as the number of unknowns. So for, like in this example, we have two equations into two unknowns, which means that we will have a single solution if they are independent. The linear equations, they are independent. Okay, and this is important to remember. And now we let us talk about some other very important topic in linear algebra, is the determinant of matrices. What is the determinant of matrices? Okay. Okay. If you have any matrix A, okay, so the determinant of matrix A, usually it is represented like determinant of A. Usually it gives like a single or a scalar. So the determinant of matrix A is a scalar, okay, or it can be actually in some special cases can be even like a complex number, especially when we have like ill-conditioned matrix. This we will come later about it. But in general, that the determinant of matrix A is a scalar, okay, and it can be positive or it can be negative actually, okay, and also it represents the volume or the area by the space formed by matrix A. What this mean? If you have let us that you have a matrix A which is 2 by 2, okay, so when we have matrix A which 2 by 2, let's say it is 1, 2 and 2, 5, for example, okay, so now this matrix can be represented into two dimensions, okay, and the determinant of A will be the area of the parallelogram represented by this form, okay, and the determinant of A, sometimes it is represented like determinant A, or it can be also the magnitude value of A is equal to, in this 2 by 2 matrix is very easy to find. You just multiply 1 by 5, the main diagonal, 1 by 5 is 5, minus the other diagonal, so it will be 1 by 5 is 5, minus 2 by 2 is 4, so the result is 1. So the determinant of matrix A in this case equal to 1. In general, for a matrix A equal to, let's say, A, B, C, D, the determinant of matrix A is equal to A times D minus B times C. This is the determinant of matrix A in the two-dimensional matrix. Okay, in a three-dimensional matrix, it can be a little bit more like tricky to find, and as we can see. So if we assume that we have A, okay, of course you can find the rule, the rules to solve it in books, but here I will make it like over some numbers. So it is assume that it is 1, 2, 3, maybe 0, 0, 1, 1, and let us put here like 2 and 1 and 0. Okay, now if you want to find the determinant of A, the determinant of A, if we take the leading row, if we take this row as a leading row, so you put simply you can change the signs like positive, negative, positive. Remember this: positive, negative, positive. So you take the first element 1, okay, then this one, when you take this one, you remove the column with this one and the row with this one, and you take this matrix. So this matrix is called minor. This matrix is called minor. So it becomes like 1 times the determinant of this matrix, which is 1 1 1 0. Okay, then we take the second element. The second element is 2, but which, as I said, we change the sign, so it becomes -2 times what? Times the determinant of the minor of 2. What is the minor of 2? We remove both of those. It will be 0 1 2 0. It will be 0 1 2 0. Okay, and finally plus 3, and we take the minor of this 3, which is 0 1 2 1. The determinant of 0 1 2 1. Okay, and this could be found like 1 times the determinant of this matrix, of this minor, is 1 times 0 is 0. 0 minus 1 is -1, so it becomes -1. Then -2 times the determinant of 0 times 0 is 0. 0 minus 2 is -2, so it becomes like +4. Yes, +4. And finally, it becomes plus 3 times this determinant. 0 times 1 is 0. 0 minus 2 is -2. It becomes -6. Okay, and then the result will be -4 plus 3 is +4 is 3. 3 minus 6 is -3. So the determinant of this matrix is -3. Okay, this is the way. What if you have 4 by 4? It will be a little bit more, not complicated, but it will be like more lengthy in this case to solve, because what you will need to do is to take the leading element, and then you remove the column and the row where is the leading element, and then you take the minor. The minor will be in this case 3 by 3, and you take it again to become like 2 by 2 to become solvable in this way. Okay, so it can be quite lengthy, but of course we have a lot of efficient and easy numerical techniques to find the determinant of matrices, and actually no one need to do it by hand, just to understand what is the operation done here. But in general, we have packages that they can solve them efficiently. However, remember that the determinant, for example, if you have matrix A, which is 3 by 3 as this one, so the absolute value of the determinant, so the determinant of any matrix A 3 by 3, the absolute value, it will represent the volume of the box represented by the eigenvectors, the box of the column vectors of this matrix. Okay, what if you have a matrix A with n by n? Then the determinant of this matrix, the absolute value of the determinant, again will be, or will represent the n like volume of the box represented by this or by the column vectors of this matrix A. Okay, so this is quite general, the description about the determinant. So the determinant, actually we will use them in a lot in machine learning. So you should be able, or you should be familiar with the determinant of matrices, and also what they mean. Okay, what is the meaning that the determinant of matrix, and this is actually the conclusion, and this is very important. What is the meaning if the determinant of matrix A equal to 0? Okay, for any matrix A, if the determinant is equal to 0, it means that it is not full rank. It is not full rank because the determinant first is defined only for square matrix. Okay, so the matrix should be square, like n by n, 3 by 3, 4 by 4, and the determinant of the matrix, if it is 0, then it means that it is not full rank. So it is one test that you can done for a matrix. So if its determinant is 0, then you know that there is linear dependency between rows or columns. Okay, So this is important to remember. Let us go to the previous example that we saw about matrix A 2 by 2, when we said that it is, for example, 3 and 5. Okay, and if we multiply this by 2, so here we will have 6 and 10. Okay, calculate now the determinant of this matrix. So the determinant of this matrix, actually A, is equal to the main diagonal, you multiply them, 3 times 10, minus the other diagonal is also 5 times 6, so 5 times 6, and you can see that the result is 0. The result is 0. Okay, because 3 times 10 is 30, minus 5 by 6 is 30, so 30 minus 30 is equal to 0, which means that A is a singular matrix, or A is not full rank in this case. So the determinant of a matrix represents the rank of it doesn't represent the rank, but if it is not full rank, so the determinant will be always 0. Okay, so this is important to remember. Also, the determinant of A, actually, when it is very small value, it means that we will have some like computational errors in order to find the inverse of the matrix, as we will see later in this course. Okay. Yeah, so now I will come to the last important part in this course, or in this session, and it is very critical part. Okay, now we said that when we multiply for any matrix A by vector x, then the impact of A, it will be the mapping of x into the space of A, and then we will have matrix or vector B, and B is a scaled and rotated version of x. So x will be rotated and scaled according to the matrix A, because it is a projection of x into the space of A. Okay, this is interesting to know. And now, what if when we put matrix A and we multiply it by vector x, we got a vector which could be represented by a scalar lambda times x itself. Actually, this is the key point of one of the key points, or one of the key equations in linear algebra. Ax equal to lambda x. What is the conceptual mean? As I said, that it is maybe it is easy to solve, to find the eigenvalue and eigenvector, but here we try not only to solve them, to compute them, we try to understand them. So it is more important when we deal in deep learning and machine learning. We should understand what is the meaning of that. Okay, so if you look to this equation, Ax equal to lambda x. Lambda is a scalar. Okay, and x is a vector, is the same vector here. Okay, if you remember, we said that x for any vector, this was in session 1, we said that for every vector represent a magnitude and phase, or direction. Actually, it has magnitude and direction. So if you have any vector x in 2 dimensions, for example, it means that it has magnitude, this is the length, okay, and it has also direction represented by theta or phi. And in 2 dimensions, for example x1 and x2, we know that the length is square root of x1 square plus x2 square, and the angle phi, or the angle theta, is the tan inverse of x2 divided by x1. So we know that. Okay, and now this x represent the magnitude and phase. However, look to this equation. Ax, maybe A is not clear. If you allow me that I write it in better way. Okay, so it is I make it bold. So it is general, of course. It is n by 1, n by n. Vector x is n by 1, and then this one is n by 1 as well. And lambda, of course, is 1 by 1 because it is a scalar. Okay? Now, you can see that the length here, the length of vector x is not important. The length of vector x is not important as far as it is not 0. Why? Why it is not important? Because actually you can multiply both equations by any alpha, any scalar value alpha, and then you can scale the length of x, because alpha, it can cancel alpha, it is a scalar also. Okay, so if you multiply alpha to both sides, then you can scale them. I give you example. Assume we have a matrix A multiplied by vector. Let us say this x vector is 1, 2, 3. Okay, and now we got lambda times 1, 2, 3. Okay, and now if you like divide, okay, if you divide both sides, or if you multiply both equations by, let's say, half. Okay, if you multiply here by half and you multiply here by half, nothing changed, the equation is still valid. Okay, but now what we will have, we have a times, it becomes half 1 3 divided by 2, it will be the same, lambda, okay, half 1 3 divided by 2. If you multiply both equations by 3 or by 10 or by 50 or by -1 or -2, whatever that you multiply those equations, it will not change. The same concept will valid. So ax equal to lambda x is valid regardless of the value of the length of x. So actually we can design x, for example, to be the length is 1, for example, or the length is 2. It doesn't matter. Okay, so what this mean? What is the concept of that, or what is the physical meaning of that? The physical meaning of that the direction of x when you map x into A will not be changed. So if you have certain or special kind of x that you multiply it in a matrix A, and the result will be the same x. Of course, it is scaled by lambda, but it will be the same x. Okay, then we call this x as the eigenvalue of matrix A. Is the eigenvalue, the eigenvector of matrix A. X in this case is equal to the eigenvector of A. Okay, x is the eigenvector of A because the mapping in A will not change the rotation or the face or the direction of x. It means that x is the same or is one of the bases of A. X is one of the bases of A because for every matrix A, it is like a space which has bases. It has bases. For example, if A is 2 by 2, and A is full rank, then it will have like a space with 2 dimensions. But the two dimension of A is not as the original one. This one. What is the dimension? What is the matrix A represents the original one is the identity, as I said, 1 0 0 1. Okay, but for general matrix, let's say 1 2 minus 1 3, for example. Okay, so the basis of this matrix is not this space. It will be another basis. Okay, how to find the basis? The basis will be the eigenvalue, because the eigenvalue, when it is multiplied by the matrix A, the matrix A will not change the direction of x. Will not change the direction of x. When it is not changing the direction of x, it means that x is one of the bases of the matrix A. Okay, one of the when we have like 2 by 2 matrix and it is full rank, then we should have 2 bases. We should have 2 bases for that. So it means that we have 2 eigenvectors. Okay, but we can have also 2 eigenvalues, because the eigenvalue is the scale of that eigenvector. The scale in that direction of that eigenvector. So in general, when we have A, let's say A is a 3 by 3 matrix, okay, and it is full rank, then we will have a 3 eigenvectors. So it will be like x1 equal to lambda 1 x1, okay, A times x2 equal to lambda 2 x2, and A times x3 equal to lambda 3 x3. It means that we have 3 eigenvectors and 3 eigenvalues. Of course, it is not necessarily that all the 3 eigenvalues will be like real numbers, and it is not necessary to be distinct. It can be also repeated, but this is another topic that we might discuss it later. But now in general, we have like this concept. So for a full rank matrix 3 by 3, we will have 3 eigenvectors. Every eigenvector represents one of the bases of this matrix A, and it has also like a length or a scale in direction of x1 is represented by the eigenvalue. And in this case, we call this eigenvalue, or we said eigenvalue lambda 1 is the eigenvalue associated with the first eigenvector x1, and lambda 2 is the eigenvalue associated with the second eigenvector x2, and lambda 3 is the eigenvalue associated with the third eigenvector x3. Of course, some books you can find that instead of x they use vector u to represent the eigenvector, or it can sometimes they use vector v. So it doesn't matter actually. It is not matter of symbols, that it is general. In general, for any matrix A, time if we have a vector u or v or x equal to lambda times u, directly you know that this u should be or must be the eigenvector of the matrix A, and this lambda is the eigenvalue of that associated with that eigenvector. So this is important. In the next session, actually, I will start with some numerical, simple numerical calculations, how to solve to find this eigenvalue and eigenvectors. It is very important not just to understand what they mean, but it is very important in this course to try it yourself, to solve some of them yourself. Of course, we will have them also in the quizzes and the homework, because when you do it yourself, then you can see more what we mean about these concepts. Thank you very much, and see you in the next session. Thank you.